All right, AP Environmental, we're going to continue with topic 6.6 today. This is kind of the second part of it that deals with half-life and radioactive decay. Now, for those of you that have a pretty strong chemistry background, I'm going to guess that you covered this in either a regular chemistry class or maybe even you covered it in honors chemistry. I know you cover it in honors chemistry because I used to teach that class. If you're taking AP chemistry, you definitely should have covered this probably multiple times in your life. So hopefully this is kind of a review of these topics, but it is something that for the AP environmental exam, they do expect you to know. So let's go ahead and start just with a definition of what half-life means, right? Half-life is a certain amount of time that it takes for half of a radioactive isotope to decay. Now, that word decay means to break down, right? So it's going to decay into something more stable. So essentially, like, in chemistry, if you have something that's unstable and it undergoes decay, it will turn into something more stable. All right, here's a really good example of something that is unstable and it will undergo decay and turn into something more stable. So this is uranium-238. This is an isotope of uranium. I know yesterday we talked about uranium-235. That's another isotope of uranium, but I mean, whatever. There's a whole bunch of different radioactive isotopes. So uranium-238, because it's radioactive, it will decay into something that's more stable. Now, in this case, what it decays into is something called thorium-234. It's a completely different element, has a completely different mass number and atomic number. But when uranium decays into thorium, it will also release this. All right, this is an alpha particle. You might remember from chemistry, there's alpha decay, there's beta decay. You don't have to remember all those things, but this is a form of radiation. So in the process of decay, radiation is given off. All right, some forms of radiation are stronger than others. Alpha is probably the weakest type of radiation that there is, but there's other types of radiation like gamma and things like that that are a lot stronger. Okay. Now, the thing about this decay is it takes time. Some radioactive isotopes decay in a matter of minutes. Some decay within a matter of days. In the case of uranium-238, it takes 4.5 times 10 to the ninth years for it to decay by half. That's what half-life is. 4.5 times 10 to the ninth is 4.5 billion years. So let's say, for example, let's say this, I don't know, this calculator here. Let's say that this calculator was made out of uranium-238. It was just pure uranium-238. So this calculator, which is made of uranium, it would be decaying right now. It's turning into thorium. But it doesn't happen instantaneously. If this calculator was made of uranium-238, this thing is made up of trillions and trillions of atoms. And those uranium atoms are turning into thorium atoms. But as they're doing that, they are releasing radiation. So the type of radiation that's released, could be really dangerous. It could be really low levels of radiation, but regardless, it would be releasing some form of radiation. But this little statement here says if you start with 10 grams of uranium, so let's say that this calculator weighed 10 grams, After 4.5 billion years, you're going to only have 5 grams of it left because half of it will have decayed into another isotope. So this is sort of what it means, right? So let's say here is a sample of uranium, right? After one half-life, in this case, 4.5 billion years, half of it will decay. So the green here represents thorium, the thorium-234. The red represents the uranium. After another half-life, right, 4.5 billion years, half of that remaining uranium will decay. So that means you only have 25% of the original mass. 75% of it is turned into thorium. After another half-life, half of what's remaining will decay. So you only have 12.5% left of what you originally started with. So all we're really doing is just dividing it by 2 every single time. Okay. So that's essentially what half-life is. This is showing us half-life in sort of a graphical representation. This is a different isotope. This is carbon-14. Carbon-14 is radioactive. It says here it has a half-life of 5,730 years. So every 5,730 years, it will decay by half. So we have these two axes here, right? We have the x-axis, or sorry, the y-axis and the x-axis here. On the x-axis, it's showing you the number of half-lives. So we start with 0, right? We have one half-life, which is 5,730 years. We have the second half-life, which is another 5,730 years, on and on and on. On the y-axis, we have the percentage of carbon-14 that remains. So at 0 half-lives, right, we have 100% of our material. Let's just say it's 10 grams, right? After one half-life, look at what happens to that amount of carbon-14, right? We only have 5 grams left after one half-life, which is 50%. After a second half-life, you have 2.5 grams left. 25% of what you originally started with, on and on and on. Now, what I want you to understand about this decay, if you look right here where my cursor is, these are kind of roughly representing carbon-14 atoms. So let's say this is the amount of atoms that you start with 0 half-lives. Well, after one half-life, half of these original atoms here are gone. They've turned into something else. So this is the amount of carbon-14 atoms that still remain. It's half of what you started with. After another half-life, only half of those atoms are left. And then another half-life. This will continue to decay until you get down to the final atom. And then when that final atom decays, then it's done. All right. But as long as it's decaying, it is giving off radiation. But over time, there's less radiation that's given off because there are less radioactive atoms that are left. All right, so hopefully that makes some sense to you. All right, this is another graphical representation. This is just with a bar graph. So let's say, for example, this red bar here, this represents, let's just say it's carbon-14 again. So you have 100% of your carbon-14, that's your parent material. After one half-life, you have 50% of that carbon-14 left. The other 50% is some other atom that carbon-14 is turned into. Okay, after another half-life, 25%. So again, you kind of see this decay like this. All right, kind of shows you it's kind of a similar thing that we see here, right? This is just a line graph. This is just a bar graph representation. Okay, but eventually it will all decay into a more stable isotope. All right, let's do some sample problems here. Polonium-210. This is another radioactive isotope. This one has a relatively short half-life. This one has a half-life of only 138 days. So every 138 days, polonium-210 will decay into another isotope, another stable isotope. Don't worry so much about what it decays into, it just decays into something else. So what I want to know in this first question is how much, fractionally speaking, of a given amount of polonium-210 will remain after 552 days. So if this calculator is made of polonium-210 and I just let it sit here and I come back in 552 days, how much of it's going to be left? That's what I'm asking you. So the first thing we have to figure out is how many half-lives went by. Well, 552 divided by 138, which is the half-life, is 4. So that means that 4 half-lives have gone by, right? Well, after one half-life, half of it's left, right? Fractionally speaking. After 2 half-lives, a fourth is left. After 3 half-lives, an eighth is left. After 4 half-lives, 1/16 would be left. So the answer to this is after 552 days, 1/16 of the original amount of polonium-210 will still remain. Another way to say that is 15/16 will have decayed. So hopefully that makes some sense. You can look at it either way, but 1/16 remains. All right, next question. How many days are required for 7/8 of a given amount of polonium-210 to decay? So let's think about this for a minute. 7/8 of it is going to decay. Well, another way to say that is that 1/8 of it is going to remain, right? So if 1/8 of it is going to remain, that means that 3 half-lives will have had to have gone by, right? Because after one half-life, a half of it remains, 2 half-lives, a fourth of it remains, 3 half-lives, an eighth of it remains, or 7/8 of it has decayed. So all you have to do is know that, okay, polonium, has a half-life of 138 days. So if 3 half-lives have gone by, or I should say 138 times 3 is 414. So 414 days have gone by for 7/8 of a certain amount of polonium-210 to decay. All right, now this one we actually put a measurement to the amount of polonium that we start with. So it says how much of a 0.75 gram sample of polonium-210 remains after 276 days. So again, we go back to 276 days. Well, I mean, how many half-lives is that? Well, that's 2 half-lives, right? Because 276 divided by 138 will give you 2. So if we're starting, in this case, with 0.75 grams, so we have a measured amount,